In this lesson today, we're going to talk about properties of logarithms. So the definition of a logarithm is if you have log base b of x, that's equal to y, and then we call this logarithmic form, right? And then if we want to change that into its equivalent form, that's exponential form. So remember that we always use the base here. The logarithm, when I say logarithm, you say the logarithm is equal to an exponent, right? Is equal to, so b to the log of, or sorry, b to the power of y is equal to x. And so that's going to be really useful moving back and forth. Now, whenever we see log of m, what do we have? What's the implied base? Yes, so that's log base 10 of m. What about ln of m? That's log base what? E. And so those are the two most common bases that you can find on your calculator. You have log, it's base 10, and a good reminder of that is the inverse of that is 10 to the x. Remember, the inverse of exponential is log, and our number system is base 10, so that's probably why that's the most common one. Then you have ln, which is the natural log, and that's base e, and you can see the inverse of ln is right above it on the calculator. Using the second key, you can get e to the x. Okay, if we want to evaluate, we were talking about, you can use your calculator for this, or you can think about the definition of logarithms and how you can switch it back to exponential form. So this is saying log base 10 of 100 is equal to what? We can use our calculator here, but let's just think this through. So this is saying 10 to the what power equals 100. Does anybody know what answer we should expect there? 2. And let's just confirm that on our calculator as a way to check. So we have log of 100, and we expect that answer to be 2. And the reason why this is useful to use our calculator here is because if I say log base 10, that's the implied base, of 90, that's the same thing as 10 to the what power equals 90. Well, we don't have a nice clean integer exponent for that. So if I want to do that, I will need to do that on my calculator. Log of 90 is 1.95. Now we wanted to round to 3 decimal places. So what number would you round to? 1.95. Would the 4 stay a 4? And why is that? Exactly. We look to the number next to 4, which is 2. If that was 5 or higher, we'd round up. If it's below 5, we're going to round down. And then ln of 100 means e to the what power equals 100. And again, that's not going to be a very nice, clean whole number because e, remember, we talked about as being irrational. So if we just, on our calculator, type in ln of 100, we would get 4.605. And would we round the 5 up or keep it the same? Keep it the same. Very good. Okay, so this is the exponent. And by the way, you can also do a check here too. If you go second ln, you get e. And then if you go second ans, you type in that answer, you should get back 100. So that would be a way to check it as well. Okay, we want to match the graph with the function. So thinking about, if we look at this function here, f of x is log base b of x. Can you tell which one of these functions is going to be log base b? Or which one of these graphs looks like the logarithm that we were graphing the other day? B. Yes, so we have the logarithmic function. It has the asymptote happening here at x equals 0. So log base b, this is going to be graph b. And then what about this one, b to the x power? What kind of function is this if we have the variable in the exponent? Exponential. And they're saying that the base is greater than 1. So is that going to be exponential growth or exponential decay? Growth. And which one of these has exponential growth? C, good. And then the last one, well, process of elimination, right? But this one that we call exponential growth. And so the last one is saying which one should be b to the x if b is in between 0 and 1. What numbers did we say are in between 0 and 1? Yes, proper fractions are in between 0 and 1. So this is going to be an example of exponential decay, and it has to be a because there's only one left, and that's what it is. So exponential decay. Now let's look some more at some of the properties of logarithms, and we might start to see some rules emerging here. So for the first line here, this says log base 10 of 10. Now, if we go back to that idea of exponential form, this is saying base of 10 to what power is equal to, and this is the power here, is equal to 10. So what would you say the exponent would have to be? 1, exactly. Notice here, log base 5 halves of 5 halves, what do you think the exponent would have to be? What's the exponent on 5 halves that gives you 5 halves? Also 1. Log base 24 of 24, you're starting to see a pattern here. What do you think? 24 to what power gives you 24? 1. So essentially we can make this rule then. The log base of the base is always equal to what? 1. And that's because b to the first power is equal to b, right? What about this one? Log base 10 of 1. So again, this is saying 10 to the what power is equal to 1? 0. 10 to the 0 power is equal to 1. 5 to the what power is equal to 1? Also 0. 24 to the what power is equal to 1? Also 0. So if we say we can come up with a rule then all the time whenever we have log base of 1, it's always going to be equal to 0 because the base to the 0 power equals 1. Okay. Let's go to the next one. Here we have log base 3 of 3 to the 7th. So again, this is asking us 3 to the what power is equal to 3 to the 7th? Can you see which power it would be? It would have to be 7. So you can almost think about log base 3 and 3 as inverses of each other, 3 to the power of, right? So the log base 3 undoes the 3, giving us the exponent left. So here, if we say base to what power equals base to the x power, always these are going to undo each other, leaving x. And that's sort of the idea, I mean, that really is the idea of the inverse, because they undo each other. So the same logic here would apply. If log base of the base is its inverse, you know, leaving here 1 or leaving x, the exponent, what do you think 9 to the power of log 9 is? 1. But in this case, it's 17 because that's what's inside the log base of 9. b to the log base b of x, therefore, is going to be x. And we were kind of talking about that when we were talking about finding the inverses and checking. You can think of 9 to the power of log base 9 as being inverses of each other, the same way you can think of log base 3 as the inverse of 3 to the power of something, depending on whatever that number is, or variable. Okay. Any questions so far on that? Yes. Okay, let's go back up here. Well, graph C is, oh yeah, graph A, why is this exponential decay? Because it's like what we were talking about last time with half-life. What's happening is your numbers are getting smaller and smaller and smaller as x goes to infinity. So therefore, whatever your number is decaying. And we saw that with the example you brought up in Connect Math as well. When we see that you have a base that's a fraction, then as you take a fraction, like let's say we had, for example, let's make an example, h of x equals 1/2 to the x power. If I keep taking bigger and bigger values of x here, let's say it's, well, even squared is 1/4, right? If I replace the x with a 2, I get 1/4. That's going to get really, really close to 0. If I did x to the third power, or I mean the x was 3, then I would have 1/2 to the third power. That's going to be 1/8. So as x gets larger, we start to see that asymptote happening at y equal, the equation y equals 0 is the x-axis. Okay, good question.